Hello, everyone. I'd like to walk you through my internship experience at A-Star I2R, where I worked on using large language models to generate and evaluate math word problems for primary school education. I'll cover what I built, what I learned technically, and what this experience has taught me beyond code. So I was attached to the Institute for Infocom Research, or I2R, under A-Star. Specifically, I joined the AI for Solution program, a 5-year joint research initiative between I2R and National Institute of Education, which is funded by the MOE Science of Learning grant. The program is building an integrated AI-driven educational platform with 4 main pillars. Firstly, a tutoring application for students. Secondly, an authoring application for teachers. Thirdly, a teaching analytics dashboard. And lastly, a unified platform that ties all these applications together. So my work sat squarely in the second pillar, where I helped develop the authoring application for teachers. So as a research intern, my role was to develop the AI workflow that powers content creation for the math authoring application. I was generating math word problems aligned with the primary school MOE curriculum, and just as importantly, generating the structured representations for these problems that the math tutor uses to scaffold the student learning. The work was research in nature, meaning we often had to define the problem ourselves through literature review, discussion, and a lot of trial and error. So my work broke down into 4 subtasks. First, generating math word problems with large language models. Secondly, evaluating those generated math word problems for quality. Third, generate structured representations for each of the problems for the tutoring application. And lastly, evaluating those model structures. So by the end of this internship, all 4 blocks were then integrated into the math authoring application. So let me walk you through each part, starting with the MWP or math word problem generation and evaluation. So there are 2 main challenges when we are trying to tackle for our math authoring application. Firstly, large language models tend to produce mathematical inconsistencies and problems that are not exactly aligned with the MOE curriculum. So this is due to its biases when it's training on its dataset. Now we want to create math word problems that are fast and catered to the MOE curriculum. But if we are able to generate lots of math word problems, we run into another difficulty, where we instead spend a lot more time evaluating each math word problem, whether they are valid or not. So we need to somehow automate both generation and evaluation of math word problems to be aligned with the standards of the MOE curriculum in an efficient manner. So for generation, the prompt was structured around 3 components. Firstly, we have input parameters like model type, number of digits, and the real-world context. Secondly is the model type definitions, which we have embedded examples inside the prompt. And lastly is the generation criteria rule set. So the goal was to give context to constrain the large language model's output space, enough that it would be reliably producing math word problems matching the MOE curriculum without losing the creativity that it's built into the large language model biases. So the first technique that I used is few-shot prompting. We gave the model a handful of carefully chosen example inputs alongside the expected math word problem to be generated. So without those examples, the model will not be able to differentiate between the model types. Now with them, it imitates the form, the tone, and more importantly, the structure of real curriculum problems. The format consistently improved immediately, and the vocabulary started matching MOE phrasing, and the rule interpretation errors dropped. So few-shot prompt engineering technique is the cheapest, most reliable way to anchor the style of the large language model. Another technique I use is the chain of thought. So before producing the problem, we ask the model to reason step by step against a criteria. So the reasoning trace becomes a self-check. If the mathematical operation is wrong, or the digit count is off, or even the sub-questions don't share the same variable, the model catches it and rewrites the whole method problem. So this single technique actually fixed a lot of cases, particularly when a subtraction math concept request was coming back as a division problem because they had the same model type names. And other times where we had 4-digit ask, and then we get back a 3-digit method problem. So the trace inside this prompt actually helps users see the corrected output. So the last prompt engineering technique I have applied is the self-critique. So after each generation, I added one more turn where the model audits its own output against the criteria checklist. So if anything fails, whether it be model type, number of digits, we prompt it to regenerate the failing component and audits it again. So actually it becomes much more cheaper than running another API call for an evaluation and catches it for any obvious failures. So to me, the big lesson here was that none of these three techniques is sufficient on its own. So if we anchor reasoning and review on top of one another, this combination actually produced more consistent method problem outputs, which we needed. So for evaluation, I built an LLM as a judge framework. The judge takes the same 5 inputs and the generator received plus the generated problem and outputs a pass or fail with reasoning across the 13 distinct criteria. So these 13 criteria fell into 3 main categories. Again, it will be the mathematical constraints. So things like whether the model type, number of digits, and connectivity between sub-questions are valid. The plausibility constraints, whether the number and scenarios given in the method problem are realistic. And lastly, the language constraints. So whether the method problem is concise, whether it is with clarity, and there are no ambiguous numerical information given. So splitting the 13 criteria into these distinct categories let me give the model targeted context for each judgment, which reduced hallucinations substantially. To test this, I built a benchmark of 180 hand-curated method problems and used precision and recall metric to track the performance across 4 state-of-the-art models, namely Anthropic models, ChatGPT models, Gemini models, and Qwen models. The mathematical constraints exceeded 90% on both metrics, and the LLM handles them pretty well. Language and contextual criteria also scored very high. Where the models struggled was on the number and scenario plausibility. The LLM couldn't always reason, say, a cyclist traveling at 485 kilometer an hour is actually physically unreasonable. So this matches recent research showing that LLMs operate on a text-based common sense and struggle with physical world reasoning. Now, a real production problem. Generating one method problem and its evaluation through the API call took almost 3 minutes, which is completely unsuitable for a teacher just pressing a button in real time. My first instinct was knowledge distillation, which is to train a lightweight open source model from a teacher model, typically a state-of-the-art model. But that needed a lot of GPU resources and training time, which we didn't have. So I stepped back and asked, instead of optimizing the models, can I optimize the structure of the pipeline? So the three evaluation prompts didn't actually need to run sequentially. They could run in parallel. So I refactored the independent API calls to make them call concurrently and brought generation and evaluation down from 3 minutes to a single minute for each method problem. To me, that was probably my biggest single lesson. So when you're resource constrained, sometimes the best fix actually beats the algorithm. So the second half of my work was on the structured representations. So the JSON files the tutor app uses to scaffold the problem solving with Polia's four-step method. A common theme in classrooms is the lack of structured reasoning. At times, teachers go straight to the answer to the problem. So we do not want the students to feel stuck with memorizing solutions. Instead, we want students to learn how to solve math word problems with a structured set of thinking. To address this, the tutoring application introduced a structured representation to scaffold problem solving using Polia's four steps framework. So in the tutoring application side, we now have to generate these guiding questions and answers to help students understand key concepts for teachers and misconception amongst students. So each method problem gets three structured components. We have asking for a number, AFN questions, which guide the student to identify numerical information in the method problem. The second one is the wanted MCQs, which ask the students what the unknown is that the question is asking the students to find. On top of this, we need to generate distractors based on common student misconceptions. And for the last one, we have model structure and relationship MCQs, which walk them through how the unknown quantity that is being asked is connected to the given numerical information. So the whole point is to make students think alongside with AI rather than passively consume its outputs. So one thing I learned for the prompt was that not every prompt needed to have the same complexity. For instance, the asking for a number prompt was deliberately kept concise. I only included the task definition and population instructions. There was no need for fancy prompt engineering techniques such as few shot or chain of thought. As for relationship MCQs, where the model need to extract structured fields and generate meaningful distractors, I had to use chain of thought alongside with few shot. So this part specifically taught me to not overcomplicate the solution and actually match the prompt strategy to the difficulty of the task. The third major piece of work is where I learned the most about real product development, which was integrating all of this into the math authoring application front end. So previously, the only way for teachers to use the app is to manually pass the JSON files into the application. I integrated the LLM generation and evaluation services using Fast API, so teachers could just generate content with one button click. So regenerating specific problems, flag field criteria in the end, and filter content into a JSON file. To me, the interesting moment was when generating a 4-digit by 2-digit long division broke the UI. It caused excessive scrolling and overall poor user experience. So that bug taught me how tightly backend logic and front-end constraints have to be aligned in this case. Now, I want to speak back from the project itself and talk about what I have learned both from a technical skills and a personal skills point of view. So for technical skills, I learned prompt engineering as a core skill in this internship. I came in thinking of prompts as instructions, but by the end, I thought of them as design of conditions under which the model is most likely to reason correctly. So in this case, few short anchored representations, whereas chain of thought encourage deliberate reasoning, self-critique caught errors before they even reach the user. So even the combination of the different techniques such as chain of thought and few shot learning allowed models to mimic human-like reasoning. To us, this is useful when giving instructions to models on how to evaluate math word problems as teachers. As for the other lessons learned, the integration work taught me that back end and front end live in a feedback loop. So a change in how I structured a JSON response could break the teacher's workflow. A UI constraint could force a back-end redesign. So this required me to work and communicate with the front-end developer and fully understand the other's problems and needs. At times, I had to include specific fields in my JSON file for the front-end developer to use, such as fields to manage the current sessions in the math authoring application. I came in seeing backend and frontend as separate domains, but I live seeing them as actually one continuous system. So on the soft skill side, to me, the biggest growth came from learning outside the lab. So my supervisor, Dr. Liu Gui Mei, actually encouraged me to attend technical seminars in NTU, where I attended a seminar series on theoretical frameworks for reliable AI systems, to even applied AI events at Lorong AI, where I get to talk to MWE educators practicing AI in their own teaching. Uh, I saw teachers creating their own slides using ChatGPT 5.2, and it was really eye-opening. I was able to self-study model context protocol through Anthropic Academy as well. So the habit of seeking out knowledge beyond the project scope is something I want to carry forward because the field of AI moves too fast to wait for someone to teach you. Another lesson I've learned is communication was important. So in a research team where we had weekly sessions working on teaching analytics dashboard and the math tutoring application, we had very little time and we had to make use of it. So you can't just show up only with the results. You have to you have to walk the team through your reasoning, your trade-offs, and your assumptions of the work you have done over the past week. So being able to clearly explain why I split the evaluator into three prompts, or even why I switched from knowledge distillation to parallel API calls, made difference between a discussion and a decision. So looking forward into my career, I'm leaving this internship with a clearer picture of where I want to go. So the future to me of human AI collaboration is agentic workflows, AI agents that can securely interact with database, external tools to execute a complex workflow. So I'm not just equipped to write prompts anymore. I'm also equipped to architect AI systems that balance generative capability with reliability and a user-centered design. That's why I'm carrying into my upcoming internship where I work on applying generative AI in the finance field this coming summer. And with that, I'd like to thank you for the amazing opportunity I have in A-Star.